All right, let's dive into something I find absolutely fascinating about AI, memory. How does a machine learn from the past to figure out what's coming next? Well, we're about to find out.
I mean, think about it for a second. You're typing a text, and your phone suggests the perfect next word. It's almost like it's reading your mind, right? How does it do that?
Well, it's not magic, but it's pretty close. It's actually a special kind of AI that has figured out how to understand sequences. It knows that the order of your words makes all the difference, and it uses that context to make a really good guess. And let me tell you, that's a huge challenge for a computer, but it's one they've gotten incredibly good at solving.
So, to really get how they pull this off, we first have to talk about a pretty fundamental hurdle in artificial intelligence, the memory problem. Because for so many things, context is, well, it's everything.
A standard neural network, what they call a feed-forward network, it basically looks at all its information in one big gulp. It has no built-in way to remember what came just a second before. It's kind of like trying to read a sentence by looking at all the words at the exact same time. You just can't get the meaning. Your brain, on the other hand, remembers each word as you go, building context. For a long time, standard AI just couldn't do that.
And that brings us to the hero of our story today, the recurrent neural network, or RNN for short. This was a total game changer in its design, created specifically to give AI a form of memory.
Okay, so you can see the key difference right here. On the right, that's the standard network we just talked about. Info flows one way, and that's it. But now, look at the RNN on the left. See those little loops? That right there, that's the secret sauce. Those loops are what let information stick around, creating a memory.
So what is that loop actually doing? This diagram is a brilliant way to picture it. It shows the network unfolded through time. Think of it like taking that loop and stretching it out into a line. The output from one step, which holds a memory of the past, gets fed right back in as an input for the very next step.
Exactly. So as the RNN processes a sequence, say the words in a sentence, it's not just looking at the current word x2. No way. It's also getting information passed to it from when it processed x1. This chain is exactly how the network builds and holds onto a memory, a context of everything that's happened so far.
But, like any great hero, the basic RNN has a tragic flaw. That memory loop is a fantastic idea, but it really starts to struggle when the sequences get long, like really long.
This leads to a huge problem called the vanishing gradient. Now, in simple terms, a gradient is just the signal the network uses to learn. When it's learning from a long sentence or a long piece of music, that signal has to travel all the way back to the beginning. The problem is, it gets weaker and weaker with each step until it basically vanishes. The network literally forgets what happened at the start of the story.
And then you've got the total opposite problem, the exploding gradient. In this case, some bits of information get over-amplified as they go through the loop. The signal gets bigger and bigger until the learning process just becomes completely unstable. The whole thing just, it explodes, computationally speaking. So, you put these two problems together, and you get a network that's great for short-term memory, but it really struggles to connect the dots over long distances. It can't figure out how something at the beginning of a long sequence affects something at the very end.
So what's the fix? Well, we need to build a better, smarter memory. And that's exactly what researchers did with an absolutely brilliant invention called the Long Short-Term Memory Network, or as everyone calls it, an LSTM.
Okay, I know this diagram looks a little intimidating, but the core idea is actually super elegant. Instead of just one simple loop, an LSTM has this complex internal structure called a cell. The best way to think about it is like a very smart gatekeeper for the network's memory. This gatekeeper has three main jobs. First, there's a forget gate. It looks at old information and intelligently decides, you know what, this isn't relevant anymore, and gets rid of it. Second, an input gate checks out new information and decides what's important enough to save to memory. And finally, an output gate figures out what part of that carefully curated memory should be used to make the next prediction.
This quote just nails it. The network can now selectively remember or forget. It's not just passively carrying information along anymore, it's actively managing its own memory. And that is the key to solving that vanishing gradient problem and finally learning those crucial connections over long periods of time. So, this all sounds pretty cool in theory, right? But where does it actually show up in the real world? Let's take a look at where this technology is already having a massive impact on our daily lives.
I mean, every single time you talk to Siri or Alexa, an RNN-style network is processing the sequence of your words.
When you use Google Translate, it's understanding the sequence of words in one language to create a new one in another. And that text autocomplete on your phone? That's it too. This stuff even powers financial models that predict stock prices and forecasts for the weather. Seriously, this technology is already all around us.
And that leaves us with this really big, fascinating question. We have actually given machines the ability to remember the past and understand context. So the real question isn't just about what they can do now. It's about what they'll learn to predict, to create, and to understand tomorrow.